Okay, today we are going to talk about section 6. We've been talking about law of sines, law of cosines, and in sections 2 and 3, we talked about how to evaluate trig functions like sine, cosine, and tangent using reference angles. Whoops, sorry, I didn't mean to cross that out. I meant to underline it. So today we're going to talk about functions that are circular and periodic. Okay, so we're going to keep finding values of trig functions. It's going to be very similar to what we did before with reference angles based on the unit circle. And then we're going to use the periodic property of some of those functions to do some evaluating as well. So there's several vocab words or phrases you should be on the lookout for in this section. So make sure that as you see those that you make sure you can define them and understand what they are. So we're going to start out talking about circular functions. And we've been talking about the unit circle some already. The unit circle is a circle with a radius of 1. That's why it's called unit, 1 unit circle, centered at the origin on the coordinate plane. So the circle that we've been talking about with all of those radians and degrees, we sometimes call the unit circle. When we call it the unit circle, we assume that r is 1 because the radius or the distance from the center to any point on the circle is 1. So instead of thinking about this point as r0, we think of it as 1, 0. It makes it really easy to calculate sine and cosine, as you'll see in a minute. Remember that in general, we say that sine is y over r if we're defining it on the coordinate plane. But if r is 1, then the sine is just y over 1, or y. Cosine we define as x over r, but if the radius is 1, it's x over 1, which is just x. So cosine of theta is x, and sine of theta is y on the unit circle. This is super handy because any point on the unit circle, its x coordinate is cosine and its y coordinate is the sine. So without even having to calculate, if I know the ordered pair, I know that the x value of that ordered pair is cosine and the y value is sine. Okay, so if theta is 120 degrees and I draw that angle in on my unit circle, then the x coordinate will have to be the cosine of 120 degrees, and the sine will have to be, the y coordinate will be the sine of 120 degrees. Both cosine and sine are functions of theta. So when we do this, we're thinking of theta as being like our x value. So cosine of x equals y, sine of x equals y. So each ordered pair is cosine and sine. Because I define them on the unit circle, they're called circular functions. They go round and round and round and round. Okay, so let's take a look at this example. The terminal side of angle theta in standard position intersects the unit circle, that's key, at this point. Find the cosine of theta and the sine of theta. So we do not know what theta is, but we know the x and the y of the coordinate or the ordered pair on the terminal side. This is so easy. We know that on the unit circle, every x coordinate is cosine and the y coordinate is sine. So the cosine of theta has to be the square root of 7 over 4, and the sine of theta has to be 3/4. We don't even know what theta is, but we know that that has to be true because it intersects the unit circle. So you guys go ahead and do the same thing here. All right, your answer in this case is A. Again, remember that x represents the cosine of theta, and y represents the sine of theta when, if and only if, we are on the unit circle and our angle is in standard form. All right, periodic functions. Periodic functions are very similar to circular functions in that they repeat patterns. They just don't necessarily have to be defined by a circle. A periodic function has y values that repeat at regular intervals. So one complete pattern we call a cycle, and the length of that cycle is called the period of the function. So if I look at this first example here, you can see that if I consider 0, 0 my starting point, I don't have to do that, but just for ease, I go up, I cross 0, I go down, and then I hit the same y value again here. So that's one example of my pattern, right? And you can see that that pattern is repeating. Here's another full cycle of that pattern. So this red represents one cycle, the green represents another cycle. The length of one cycle, 2 pi, is the period. So here this goes from the x value of 0 to the x value of 2 pi, so its period is 2 pi. If we look at this example, I look for my repeating pattern, the period here is going to be 4. So if I think about starting at 0, I go down, I do that little pattern, come up, do the pattern, and come back down to where I started. That length is 4. So that's one cycle of my pattern, and the length, or the period, is 4. Take a second to look at this function and see if you make sure you understand why the period of this function is 6 and why the period of this function is 2. Pause if you need to. All right, so we are going to determine the period of this function. The pattern repeats, starts repeating here, and then again at 2 pi over 3, at pi, and so on. So here it's like I'm starting at 0, 0, go do that little pattern, go below, do that pattern, and come back up to pi over 3. So the period is pi over 3. Every pi over 3 units, my pattern will start over. Okay, so why don't you guys determine the period of this function? Okay, the period here should be pi. If I think about where I'm starting down here at -1, I go all the way up to here and come back down. That's when my pattern starts over. So that distance is a length of pi. If I go another pi units, it starts over again, and so on. Notice that on your notes I skipped over example 3. We're going to go back if we have time, but I want to make sure that we take a look at the unit circle now with the ordered pairs. So for example, we know that pi over 6 radians is the same as 30 degrees, right? And we know that the sine of 30 degrees is 1/2, and the cosine of 30 degrees is square root of 3 over 2. So the ordered pair that this point represents is the square root of 3 over 2, 1/2, cosine and sine. I know that pi over 4 is 45 degrees. I know that the cosine of 45 degrees is pi over 2, and the sine of 45 degrees is pi over 2. So that's the ordered pair. Notice there's an ordered pair for each angle all the way around, which is the cosine, which is the x value, and the sine, which is the y value. If I look at 135 degrees, we know that the reference angle of 135 degrees is 45 degrees, right? So notice that the sine and cosine values are almost the same. The only thing that's different is the positive and negative. Since 135 degrees is in the second quadrant, my x value, or my cosine, has to be negative, and my y value, sine, has to be positive. But it's the same basic ordered pair. So notice the ordered pairs repeat all the way around. The only thing that's changing is if they're positive or negative. The other thing we want to look at is what happens if I graph the sine of theta or the cosine of theta, instead of on a circle, on more of like an xy axis, except in this case theta is like our x. So my x-axis here, if you look at this, is actually theta, and it's marked by the size of the angles. So for example, the sine of 0 is 0. The sine of 90 is 1. The sine of 180 degrees is 0. The sine of 270 is -1, and the sine of 360 degrees comes back to 0. So this is what the sine graph looks like, and it repeats the same pattern forever because it is periodic. It has a period of 360 degrees, or 2 pi radians. It works the same with cosine, just cosine starts kind of at a different place. The cosine of 0 is 1. The cosine of 90 is 0. The cosine of 180 is -1, the cosine of 270 degrees is 0, and then at 360 degrees I come back up to 1. So the cosine graph looks very similar to the sine graph, it's just shifted over 90 degrees. So this kind of top part of the bump here is shifted over to the left 90 degrees. So remember again, here theta is being measured as if it were my x-axis, that's my degrees, and my y value comes from the cosine of that angle. Now for sine and cosine functions, they're both periodic. They both have periods of 360 degrees, or 2 pi radians. So it makes it pretty easy if I want to calculate the values of angles that are larger than 360. So let's take a look at what we would do here. To find the exact value of the cosine of 690 degrees, we say, okay, I know that cosine repeats every 360 degrees, right? So I can basically take 360 degrees away from 690. Another way to say that is I know that 690 degrees is 330 degrees plus 360 degrees. So those the cosine of 330 is the same as the cosine of 690 degrees. And we should know that the cosine of 330 degrees is the square root of 3 over 2. Why? Because if we draw, sorry for the bad graph, but if we draw 330 degrees, right, that comes around to here, that has a reference angle of 30 degrees, and we know that the cosine of 30 degrees is the square root of 3 over 2. I'm in the fourth quadrant, and that is where cosine is positive, so it's positive square root of 3 over 2. All right, we're going to do the same thing here with an angle in radians. So another way to use periodic functions is to say, okay, this is a negative angle. Maybe that's a little bit harder to find the sine of. So I can add 2 pi. That's what they're doing here. They're adding 2 pi because every 360 degrees or every 2 pi radians, the sine value repeats exactly. So 2 pi is the same as 8 pi over 4. That way we have common denominators. When I add those together, I get the sine of 5 pi over 4. Now that, we should recognize pi over 4 is 45 degrees. Sorry, I forgot where I was. Okay, so pi over 4 is 45 degrees. And we know that times 5, we can figure out what that angle would be. Or, we should just know it in radians. 5 pi over 4, if I look at that on my graph, 5 pi over 4 radians is the same as 225 degrees. So my reference angle here is going to be pi over 4. So I'm asking myself, what is the sine of pi over 4? Well, the sine of pi over 4 is the square root of 2 over 2. So the sine of 5 pi over 4, because it is in the third quadrant, sine is negative there. So the sine of 5 pi over 4 is negative, square root of 2 over 2. So I want you guys to try these next two examples. All right, for the first one, you should have gotten 1/2. I'm basically thinking of this as being the same as the cosine of 300 degrees, because 660 degrees is 360 degrees plus 300, and the cosine of 300 degrees is 1/2. Its reference angle is 60 degrees. The cosine of 60 is 1/2, and I'm in the fourth quadrant, so cosine is positive, so it stays positive 1/2. All right, now try negative 7 pi over 4. All right, the sine of that is square root of 2 over 2. All right, so negative 7 pi over 4 takes us around in the clockwise direction into the first quadrant. My reference angle there is pi over 4. Another way to think of that is if I add 2 pi, or 8 pi over 4, to negative 7 pi over 4, I end up with pi over 4. So I know that the sine of negative 7 pi over 4 has to be the same as the sine of pi over 4, and we should know that in the first quadrant, that is the square root of 2 over 2, and all trig functions are positive in the first quadrant. All right, let's go back to example 3. All right, in this example, we have an example of a trig function in real life, or a periodic function. So the pedals on a bicycle are rotating as a bike is being ridden. So this picture represents a bike pedal that's going around and around in circles. The height of the bike pedal varies periodically. So it's going to go around and around in the same circle as a function of time. So as time passes, the height changes. Notice that the pedal makes one complete rotation in 2 seconds. So we're going to make a table that shows the height at 3 seconds, 3.5 seconds, 4 seconds, 4.5, and then 5 seconds. So make sure you're looking at that picture that's on your notes. At 3 seconds, the pedal would be in the same location as it would be at 1 second, because 2 seconds is its period, right? So it goes all the way around in 2 seconds. After 1 more second, it would be back here again. So its height would be 4 inches. At 3.5 seconds, it's at the same position as it would be at 1.5 seconds. So at 11, and so on. You fill in the table. Make sure you look at the picture on your notes and understand where we got each of those heights. All right, part B is asking, identify the period of the function. We kind of already talked about that. It starts repeating the same heights over and over after 2 seconds. So the period of this function would be 2 seconds, how long it takes to complete one rotation. And last but not least, we're going to look at the graph of this. The horizontal axis is going to represent time, and the vertical axis is going to represent height, how far the pedal is from the ground. So the maximum height is 18 inches, the minimum height is 4 inches, right? It goes from 4 inches off the ground to being 18 inches off the ground. So our graph is going to look something like this. After 3 seconds, at 3 seconds it's at 4 feet, 4 inches, sorry, 3.5, it's here at 11, it goes up to 18, comes back down, and it would repeat that same pattern over and over.